Hello everybody, this is going to be some solutions from section 2.6. I'll be going over problem number 10, 17, 23, 27, 31, 41, 51, 55, and 59. So you can fast forward to the problem you want, and they'll be numbered on the top left corner. So I'm starting with number 10. They want to determine where the function has discontinuities and state which. Now, don't use the continuity checklist, use the definition. I don't particularly like the checklist. So the first point you see is at 1. Where x equals 1, clearly there's a discontinuity. Why? Well, if we take the limit as x approaches 1 from the left, we're going to get 2, which is fine. We take the limit as x approaches 1 from the right, and we also get 2. Then f of 1, if we look at that, that's going to be 3. So it's not continuous because all three of these are not equal. Therefore, at the conclusion, why does it fail? Not continuous at x equals 1 because the limit as x approaches 1 from the left, which equals the limit as x approaches 1 from the right, does not equal f at 1. So that's my conclusion. Something to point out for you guys. Let's see. I don't need both of these statements here. Well, I don't need that. I can use this. I don't need both of these. I could have just did that, or I could have done just that. As long as any one of these aren't equal to another, it's not continuous. So that's number 10. Let's move on. The next one we're going to do is number 17. So 17 is asking, determine whether it's continuous at A. So for 17, we need the limit as x approaches A is going to be 1 from the left of f of x. Then we need the limit as x approaches 1 from the right of f of x. Then we're going to need f at 1. So the question is, which function do we use for the left? Well, what function, if you look at 17, to the left of 1 is going to be the top one, because that works everywhere except 1, which includes the left of 1. So we're going to take the limit as x approaches 1 from the left of x squared minus 1 over x minus 1. Well, if you do this, you're going to get 0 over 0, which is indeterminate. So we need to factor and cancel. Whoa, that's weird. It's going to be x minus 1, x plus 1. And you'll see the x minus 1's cancel. So this is the limit as x approaches 1 from the left of x plus 1, which is 2. So from the right, we have to decide which function we use, the top or the bottom. We're going to use the top again. And we have a similar situation where they factor and cancel to x plus 1, and we get 2 again, and we're happy. But for the third one, which function do we use for 1? If you look, it says when x is 1, it equals 3, so we get 3. So therefore, we can conclude not continuous at x equals 1. The reason, because, and we do the same thing, the limit as x approaches 1 from the left of f of x does not equal f of 3. Now, I could put this one instead. As long as we get a not equals, we've shown that it's not continuous. So that's number 17. Let's go on to number 23. So 23 is asking for when the function, what intervals is the function continuous? So 23, here's our function. So you have a theorem. The theorem says if you have a rational function which is a polynomial divided by a polynomial that will be continuous everywhere except when the denominator is 0. So this will be not continuous when x squared plus 9 is 0, or x squared equals 9, or x equals plus or minus 3. So these are the 2 points where it will not be continuous. So what are the intervals of continuity? It is continuous from negative infinity to negative 3, and negative 3 to 3 is continuous, and from 3 to infinity. So here's what's happening. Since there's a parenthesis here, it doesn't include negative 3, meaning it's not continuous at negative 3. And since this is a parenthesis and not a bracket, it means it's not continuous at those points at 3. So it's everywhere except 3, and that's what we have demonstrated there. Now, another way to write this, you could have written it like this: negative infinity to 3, and negative 3 to 3, and 3 to infinity. That's the equivalent way of writing it. The top is more of a set notation. The bottom is, I don't know what it's called. The bottom is the bottom. All right, that's number 23. Let's move on to 27. Evaluate the following limits. So 27, you have the limit as x approaches 0, x to the 8, minus 3x to the 6, minus 1 to the 40th. So there's another theorem. If you have a function raised to a power, you are told you could take the limit of the inside function first, and then raise to the power. Well, the inside function, you'll get negative 1 to the 40th, and that's going to be 1. So that's using the function in a function rule. That's number 27. We're going to move on to 31. 31, it's a similar thing. We have the square root of x cubed minus 2x squared minus 8x over x minus 4, and you want the limit as x approaches 4. So the limit of a function in a function, here's the rule. You can take the limit of the inside function, then take the square root, as long as the inside is positive. It can't come out negative, or we are in trouble because you can't take the square root of a negative. Well, if you plug in 4 in the top and bottom, 4 there, 4 there, 4 there, and then 4 there, you end up with 0 over 0. So a technique you learned in a previous section, when you have a 0 over 0, you have to factor and cancel. So the top factors to this, and then we have to factor again, and that factors to x minus 4, x plus 2 over x minus 4. And then those x minus 4s nicely cancel. So now, to finish this problem off, plug in a 4 here and here. You get 4 times 6, which is 24. And 24 is 2 radical 6. So that's the answer for number 31, 2 radical 6. Let's continue going. After 31, we have 41. Number 41, determine the intervals where it's continuous. So we have a function in a function. This is continuous everywhere where, okay, this is the root. This is the 1/2 power. Remember when I talked about even roots? You can't take the square root of a negative. So it's continuous everywhere. The inside's continuous as long as the inside is not negative. All right? Well, the inside is a polynomial, and you learned that's continuous everywhere. So the inside is continuous everywhere. The only restriction we're going to have is the inside must be positive. So we're going to have 2x squared minus 16 must be positive. Well, this is going to get confusing rather quickly. We're going to add 16 to both sides, divide both sides by 2. Now when we square root both sides, put in a negative 1. Is negative 1 squared greater than 8? No. It's when the number is bigger, the magnitude is bigger than radical 8. Well, where is this magnitude bigger than radical 8? It's that way. So actually what's happening is you have that region also. So when bigger than radical 8 or smaller than negative radical 8, that's where it's continuous. So where is this function continuous? It is continuous on the interval from negative infinity to negative radical 8 and radical 8 to infinity. Or if you want to do this, negative infinity coast. Everywhere except those points. If a So you might think, that's crazy. I'm never going to remember that. You need to process this. This is a common AP type question. Very common. You have to be able to see that. All right, let's continue moving on. 55 is the next problem. We will do 55. So find the interval. So again, using the rules, if you have a quotient, this is continuous whenever the top and bottom are continuous, right? Except where the bottom is 0. So we got to worry about that. Well, we know e to the x is continuous. That's something in the theorem, and we should know that by looking at the picture. And then we know 1 is continuous. Y equals 1 is a constant function. And we know e to the x is continuous. And we learn if you subtract two continuous functions, that's also continuous. So the top and bottom are continuous. So this will be continuous everywhere except where the bottom equals 0 or 1 equals e to the x. How do you get rid of e to the x? Remember you can ln both sides? So ln of 1 is 0. And ln of e to the x, those cancel the inverse function. X is 0. So that's where that's true. So here's what I want to do. Minor, how do you know that? Where is e to the x? Well, where does it equal 1? Right there, when x is 0. So you could have done that without doing this work. So our conclusion, this is continuous everywhere. Whoa. Everywhere except at x equals 0. Or another way to write this, this is continuous on the interval from -infinity up to 0 and from 0 to infinity. Or, so this is another way, or you could say it's continuous on the interval from -infinity to 0 and 0 to infinity. All of those should make sense to you. So that's the regions of continuity for number 55. And they want a couple limits here, so let's do the limits for them. They want the limit as x approaches 0 from the left of e to the x over 1 minus e to the x. Well, e to the 0 is 1. That's easy. The bottom, if this is 1, 1 minus 1 is 0, so we know the bottom's approaching 0, which is going to get us an infinity, except is the bottom positive or negative? Here is where you're approaching 0 on the left. Here. Here's 1. It's getting close to 1, but from less than 1, 0.999. So 1 minus 0.999 is positive values. The answer is positive infinity. Okay. Now let's go from the positive side. So we're approaching from the right towards 0. It's getting close to 1, but from bigger than 1. Above that's bigger than 1. So that's like 1.001. 1 minus 1.001 is negative. It's approaching 0 from negative values. So our answer here will be negative. Remember, don't write that. That's just in my brain what I'm thinking. So that's 55. I have one more to go. This is actually the second time I'm doing this recording. I just did it like an hour ago and it didn't save for some reason. This better save or I'll be very sad. Yoshida will be very sad. We're doing number 59. This is to use the intermediate value theorem to prove that 2x cubed plus x minus 2 equals 0 somewhere between -1 and 1. Wow, that got ugly there. So how do I prove that? So what's happening? This is our L. That's what we're trying to show it equals that. So first, for the intermediate value theorem to work, you have to know this. We'll call this f of x. F of x is continuous on the interval from -1 to 1. How do I know that? Because we have a theorem that polynomials are continuous. F of x is a polynomial. It's continuous everywhere. So if it's continuous everywhere, it's continuous on the closed interval from -1 to 1. That must be true. That's the first statement. The next thing, we need to find f at -1 and f at 1. We'll plug in -1, that's going to be -2, minus 1, that's -3, -5. So that's -5. Now let's plug in 1. That's going to be 2 plus 1 is 3, minus 2 is going to be 1. Bam. Is our number we're looking for, L, between these? Yes. So I must state that. Let me show you that. F of -1, which equals -5, is less than 0, which is less than 1, which is f at 1. I have shown that the number I'm trying to prove is between. So thought process, if I draw a graph, I start at -5 and go to 1, clearly you have to cross 0. That's the intermediate value theorem. So my conclusion, I've shown the two conditions that must be true. It's continuous on the closed interval, and the number you're looking for is between the endpoints. Then my conclusion is, therefore, what must be true? There exists at least one, that's not how you spell one, that's how you spell one C, and where does C have to be? Between the endpoints. Cannot include the endpoints. Between -1 and 1, such that the function evaluated at that C equals our target number 0. That's the conclusion of the mean value theorem, or excuse me, intermediate value theorem. I'm done with 59. That's it. I hope this recording will be saved and I can post it and you can watch it. All right, bye.